My old buddy in grad school is this Japanese guy who's like, oh, I forgot wallet. Every time. Uh, what's up? Okay, so we're good at all this register stuff.
I'm sorry, I don't ask a lot, but the 5.5.5.
5 point.
Please explain to me what actually being read in there. Because I was okay with the challenge thing, but.
Huh?
Yeah, he's recording.
Yeah, I'm recording. All right, so explain a 4x32 register. So four registers. A register file. So we have 4 registers with 1 read port and 1 write port. Determine our data's value at each indicated time, if appropriate. Okay. So our data is this guy. So that's our read data. So we can only read when we post write. So we wrote to, at least they made the addresses easy. So this is writing to register 1, this is writing to register 2, writing to register 3, writing to register 2, writing to register 3. In those time chunks, not all of them were necessarily, we only wrote on the upticks, and then this was the fire on the decoder that told the decoder to do its state. So the data we wrote a 24 to register 1. We wrote a 13 to register 2. We read from 1, so we read a 24.
Okay.
That make sense?
Now it does. Okay. Now I think I'm good.
Right, so,
I was looking this completely different.
okay, but hopefully, does this make more sense now after we explain the thing at the top?
Yeah.
Because we read and we write and we read. So this is where we wrote to individual registers, and this is where we read from those registers. We read from 1, we got the value of 1, which was a 24. We read from B, we got the value of register 2, which is currently a 13. We read from C, we got the value of register 2, which is still a 13. A D, blah, 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 from 3 is a 45, and still read from 3, which is also a 45, because we finished reading before we had that right. This 9 got written late. The 9 got written on this uptick, and we didn't get to this until, well, actually, the 9 got written here, so we would have read a no, we would read a 3.
For the E?
E, we're reading from 3. Here is 3. We wrote a 45. We read a 45. Not a 9. The 9 got written after we read. Just where the cycle's finished here at the end. So what did I say for B? B, I said, is registered 2, which is a 13. 3 is register C, which is also 2, which is still a 13. Oh, the read is off on C. So we're not actually reading anything. Yeah. That means we're getting the Z. That's the don't give any value. Yeah, so the Z is like the 0 but with no electricity, because we did not have an output coming off of the decoder. At the C thing here, we were choosing not to read. So we did not read anything at C. which is why we got a Z. Huh? It's Z. The answer is Z.
Because that's what it outputs?
Yeah, the output is Z, if you remember from the register, not the register, the try buffer. Yeah, the try buffer has an output of Z, nothingness, let's say. So D, we're reading, and we are reading on D and E, so we won't get tricked this time. So we're reading from 3 from both of those. So the first one will read a 45. And then the last one is where it gets a little tricky because we are writing at this same time cycle, but the when we hit the read here, we actually have not written. So we're reading at the same time as we're writing. So we're going to read the old value of the what's the old value? 3 is at 45. So we'll read a 45 instead of the 9. It's a 9. I'm writing 9. It's a 3 during cycle 5. Here's cycle 5. So this was the uptick here. Well, they're not showing us the final uptick. So during cycle 5 is when we would write a 3, and we are writing, so that would be, or write to register 3, so we'd write a 9 at cycle 5. But if that's the case and we're in cycle 6, we don't have an uptick here, so we're not technically reading. So I guess they're saying there is an uptick here, so we are reading.
So it's still 9 because the 5 weeks right 9 2.
Yeah, but we're not going to get the 9 out of it because we haven't ticked. We don't have electricity to pull it. The value's there, but we're not pulling it unless we have an uptick on cycle 6. All they're showing on cycle 6 is a down. Oh, I see. Yeah, they're showing it here. Okay.
Yeah.
Everything's on the left side of their cycle. So this is the execute. So at that point, the 9 has been loaded into 3 because the 9 was loaded into 3 during this execute here. And then, so we wrote on this execute, we read on this execute, and at that point in time, register 3 already had its 9. All right. Does that make sense? All right, you want to go through it again? Okay. Not really. All right. All right, so this is the various behaviors actually in MIPSI, but in how they are represented at the 0s and 1s level. So we have load word, we have store, so this brings into a register, this puts it into memory, this is our add immediate and our normal add. We already know what the behaviors of these are, we know what they do. But they're showing us the organization of a instruction, how instructions are broken down. So the convenient names for bit groups. So this is IR 31 through 26. So this is a 32-bit value, 32-bit instruction, let's say. That is bucket 0 through 31. So this far left thing, we have 6 bits, which is 26 to 31, and that's probably for the instruction. So we have a 6-bit instruction, which means that in MIPSI we have 64 unique instructions that we support. Then this is going to be a one of the registers. This is going to be another register, and this is probably, actually they're going to be used.
Memory?
Yeah. So it depends on the type of instruction you have. This is the 2 different kind of breakdowns for that. So yeah, this is just showing you how to read this number, like I just said. So the 31_26 is the far left 6 bits. The 0 to 5, 0 to 15 is the far right 16 bits. So leftmost instructions, this is the 26 through the 31. That's that guy. Rightmost 6 instructions, don't be fooled by the 0 to 15. It's the 0 to 5 because we're only looking at 6 bits, not. So we're looking at the last 6 bits instead of the last 16 bits. Rightmost 16 bits are 15, but these do not include the rightmost 6 bits, which already have a name. That's false. It does include them. So we get how this guy is organized. We just broke the bits up. Okay, so they're kind of showing us here in, let's call it pseudocode-ish. This is a binary value of 101011. So here they load word. This is the instruction for load word. And we've written all these things. So this is kind of just putting it together in the context of what we've talked about so far today. Is that we wrote the software version. We know what LW does. We know what SW does when you're doing MIPS assembly. Right? Then we said, okay, we know how processors are now roughly put together, where we have these register files that stuff is being written to or written to a register file or read from a register file. All right. So, and then we know that we have some math and things like that. So we talked about adders today, even though they weren't present in our processor example there. Typically, a processor would have a arithmetic logic unit, an ALU. I think that was in one of our chapters at some point. Yeah, so that's the dude that does math. So he wasn't represented in our CPU breakdown, but you know, he's there. So if we look at what this is doing, this is kind of a hybrid between like a C-like language and something else. We're saying if the instruction, that's what's in the far left 6 bits, is the LW instruction, then do LW stuff. Else if the instruction is the SW instruction, then do SW stuff. Otherwise, if it's the add-I instruction, do add-I stuff. If it's the add instruction, do add stuff. This is just a switcher. It says which function are we doing? Which instruction are you giving the CPU? As a MIPS assembly writer, we would say LW blah, blah, blah. But at the machine level, we would say we actually want the instruction 100011. Mm-hmm. That's how we say LW in binary. Mm-hmm. That's how we represent it in binary. All right, so this is machine language. This is low-level assembly code. And then high level would be, I want to load a word in English or something like that. All right, so this is giving us high-level instructions for that stuff. Yeah, so now they're giving you kind of a breakdown of this. So if you're doing a load word, this is what would actually happen. So this is direct memory A. So this is the destination. So this is the bits 1 through 25. So that, was that a 4-bit sequence? 1, 2, 3, 4, 5, 5-bit sequence. So 5-bit sequence, we're gonna load that into this variable direct memory A. This will be our direct memory offset. And then this is our register file at this location. So what does a load do? Load takes something from memory and puts it into a register. So we're saying, here's where in memory I want to go, offset by this. Now take that, and notice that we did it in terms of that. So this DMRD, this is the actual place in memory we're reading from. All right, so this is what we do if we do a load word. So we say, here is where in memory I want my value. So we're gonna get that value, and where are we gonna put it? We're gonna put it into our register file at position, that bucket, that's the address. Remember, if you go back to our register file, the input into that guy is what address, what register value you're putting this into, which then fires the decoder, and the decoder says, oh, go to register 0, register 1, register 2, register 3. Okay? So this is just an implementation of This is like a pseudocode implementation of MIPS behavior in terms of the binary instruction name. Instead of LW, we say 100011, and then this is what's actually happening. We extract pieces of information from the instruction. If we come back up here, we have the instruction. This is the 6 bits. We have a register. We have another register. Okay, and then we have whatever would go in here for this kind. This guy down here is our direct memory one that would be used for our other one. So notice that our DMA is going to give us a read from our register file, bits 21 through 25. That's this guy right here. So I'm going to pass to my register file this register. I'm going to read from that. And what I'm reading is the base address. So the base address, if you think back to MIPS, we would like store a base address in a register. Then when we actually did a load, we grab that base address and then an offset from there to get us to an actual place in memory. So give me the value from this register, store it in this variable. Then go to direct memory, give me the value that lives at this address, store it in this variable. Then we're going to write to a register. It's on the left side of the assignment operator. We read over here when it was on the right side of the assignment operator. Now we're on the left side of the assignment operator, so we're going to write to that register. What register? The one that's described in bits 16 through 20. This guy right here. So you see how these addresses, how these instructions are put together. This is the instruction. This is a register. This is a register. This is potentially another register. Yeah, these are spots that are register-sized chunks, depending on how many of you want to use. So we'll write to this register whatever value we found in direct memory. That's what load word does. We implemented that in Scheme, that exact logic, right? Ours just looked a little less scary because it looked scary because of Scheme and not scary because of zeros and ones. We still called it LW. All right, and all these other ones do the same type stuff. All right, so does this kind of make sense? All right. Yeah, this is just giving you examples of the machine equivalent of instructions that we maybe would write in MIPSy. All right. So we're good there? All right, so this is kind of giving us the bigger picture. So if we think about what we've done throughout the day, we learned about primitives, right? Then we learned about register files. We learned about adders. Direct memory, I don't think we actually had a specific thing on direct memory, but direct memory is going to work very similar to a register file. Just the hardware inside of it won't be a register. Instead, it'll be a RAM. This is the guy that kind of interacts with RAM. This is going to be our controllers. This is where we ask our questions from, and this is our program counter. All right, so notice up here, so if we kind of think about how this works, we have a variable. We had a program counter in our code, didn't we? What did program counter do? It kept track of what was the next instruction we were executing, and we took instructions in 4 byte steps. Why 4 bytes? How big is a MIPSy instruction? 32 bits. 0 to 31. The whole last chapter was on the 32-bit sequence of an instruction in MIPS. 32 bits is 4 bytes. That means we will find a new instruction. If we have a wall of binary that we're looking at, every 32 bits is a new instruction, right? So that's where we have our program counter is equal to program counter plus 4. Move to the next instruction. Okay, so this guy says, assume that the instruction has already been extracted. We just saw in the last thing that we already have the instruction. So if the instruction is an LW, is what this guy is. That's an LW. Here's the code that we're going to use for that. This is code we just looked at, right? This is the same code we just looked at. It's using this piece of hardware inside the processor. It's using this piece of hardware inside the processor for direct memory. So we're reading from a register file. We're reading from direct memory. We're writing to the register file. This guy here. All right. Store word, we're using register file, and we're writing to direct memory. So we're using this guy, we're using this guy. For add I, we're going to be bringing a value in from a register file, which is going to be RF. Then the second add value is going to be some of the bits. This is the 16 bits at the far right of our machine code. This is our immediate value. So a 16-bit value, so this would be a value between negative 32,768 to positive 32,767. Some value in that range. All right, so I'm going to add the number I found in this register to the immediate value I found in those bits. And what am I going to do with it? I'm going to store it in my register file, and I'm using add1 plus add2, so I'm actually going to use this adder right here to accomplish that. And they're oversimplifying this adder. Here's add1 and here's add2. They're oversimplifying this because they, we were introduced to an adder in the book as a 3-bit adder. Well, we got 16 bits plus 8 bits that we're adding to. If we assume it's an 8-bit register, I don't know if they even said that, but let's just assume it is. We need more than 3 bits. So inside of this, if we think about the open heart surgery thing on add here, there's a lot of adding going on under the hood, but adding's not complex. We can just trust that we can build a circuit that can add big numbers. That's fair enough. All right, so that's the that's the little tool that's being used in there. Okay, if we're doing an add immediate. So an add immediate takes the value of a register, and it takes an immediate value. We have 16 bits for representing that immediate value there. We're adding those two guys together, so this plus sign here says use this tool in here, this circuit. All right, and we get our answer, and we store it in our register file. So we're using this tool. Next, we're doing an add. Add requires 2 registers, so we are they're making sure that you actually provided it with 2 registers. Then we're coming in here, well, we're saying this is the add instruction, and this instruction 0 to 5, that's our far right bits. Is that a carry from a previous add? This might be a carry from a previous add. I'm not sure what those far 6 bits are used for in our example here. Does it tell us?
But what if it's a carry, why it must have an and?
Well, it's saying that it's the add instruction,
Yeah.
and this guy is a 1, I guess. Is actually not a 1. This guy is a 1s, 2s, 4s, 8s, 16s, 32. This guy's a 32. I have no idea what it's using those far right bits for. Does it tell me in the instruction what the far right 5 bits are?
Yeah.
That's this guy right here.
Or maybe it's just a definition.
Well, I mean, it has to have it has a meaning. It's just unclear to me what that meaning is. Yeah, so here's the example of that add with that guy down there. What does this architecture say we do with that? Does it tell us that somewhere?
I think so.
I mean, basically, as far as I can tell right now, the definition of this architecture says if you're doing an add, these last 6 bits must look like that.
Yeah,
It's the rule of the add. Okay, that's how we use those last 6 bits of the instruction to say we're ready for an add. Probably, I guess I'm making a guess here, we are using, for an add immediate, we get our value in that full 16 bits there. For a normal add, those 16 bits are split into some pieces, right? We're split into a 5-bit register, a 5-bit register, and a 6-bit whatever. So if we're not going to use this whatever, it probably has some uses in other instructions. For an add, it must have to be set like that. That's just the definition of this architecture for those last 6 bits for the machine instruction.
But I think it's because if it's set to a sub which goes through the same add, it's set to 1000010
It's possible, but that's not the way it reads to me with the if statement. The if statement here says that if I'm looking at an add instruction and specifically it's set to a 32 there, then get my 2 values from my 2 registers that I want to add together, add them together, store the result in another register. So in order to flag the way this reads, in order to flag an add, both of these conditions need to be true. The instruction must be the add instruction, and you must have a 100000 in the last 6 bits. Okay, so this is showing you how inside of a processor we are using register files, direct memory, and our ALU, arithmetic logic unit, but in this case we only know how to do addition. This is another simple processor to accomplish those things. And notice it's saying assuming that we've already extracted the instructions, so that's going to come out of this control. So the control is going to get you the instruction, and ultimately we're going to have those things feed into. So this is 26 through 31. So that's this guy right up here. So this is our instruction feeding in, and they're saying magically in here it's extracted. So something is going to go through there and peel off the first 6 bits and give you your instruction from it. And then all problems are solved in terms of your register file, your direct memory, and the adder. Go ahead. Question. Huh? We have a half hour still. Is this getting worse?
Yeah.
Yeah.
Really?
Like, I think it's time to just.
All right, so I have to do the homework real quick, then we can come back to this.
Yeah.
All right, what was the homework?
To be able to work with.
Just assignments, right? All right, so if we took in a file that looked like this, so for every definition thing here, we should spit out something that looks like this. But when we're creating a variable, we have to get our next register and our next available memory location, right? So we need those two things. So did I do this in Eclipse? MIPS compiler. All right, here's my driver. I pass it source.test, and this is in my MIPS compiler, MIPC compiler. That's in here. Okay, so I'm getting my files here. So I get my source reader. Source gives me the next line. So I'm printing out the lines. Let me just show this real quick so I can see what it does. That's not the output I wanted. I did. I tried. There we go. So here's my what? I did try to click it.
No, that's not why I left.
Oh. So we have these are my 3 instructions in my C file.
I thought they were
Oh, because I only read from it 3 times. If we go back in here. Yeah, I only read from it 3 times. So my first 3 instructions. Do I have in my source reader the ability to say, am I out of files? Yeah, get next line. This guy eventually gives me an EOF. Okay. So we'll go into our MIPS C compiler. And let's just start off with this. So we'll say, I always just like putting an infinite loop in there. It's always fun. So string instruction. So we'll say instruction is equal to next line. That's going to get us 1 instruction. I'll ask the question if, oop, that was scheme, if instruction dot equals EOF, then break. We're done. Right? So as soon as I hit the end of file, I have nothing else to do. Otherwise, process this instruction. So my instruction is one of 2 things. It's either, if I go into my C file here, where am I? I'm lost. Okay, so it's either starting with an int right now or something else, right? So I'm looking for it to start with an int. What I'm going to go ahead and do is I'm just going to split it into its parts. So I'm going to split it based on, if you wanted to make some assumptions, you could. I'm going to split this guy based on spaces. And then I'm also going to split him. Well, you can do it by an equal sign, and then you can look at the first part. That'll work.
I'm just using start with.
You can.
I
But,
did that for the int only,
yeah.
though.
So I'm going to do this. I'm going to say string array parts is equal to instruction dot split on the equal sign. All right, and then what I want to do is I want to make sure when I look at things I trim. So why does that close?
Split do exactly?
Split would give me, if I did it on an equal sign, it would give me this. So it'll give me this bucket here and this. Bucket 0 would be this guy. Bucket 1 would be this guy.
Oh, okay. So it's just saying like count buckets except for at bucket equal sign.
Yep. So that's going to give me a 2 bucket array. I know bucket 0 will exist. So I'm going to say if parts at bucket 0 dot trim dot equals int. If I'm looking at an int there, then I want to produce an output that looks like this. Add I space, I need a fresh register, followed by a comma, I need a 0, followed by a comma, I need a fresh memory location. Okay, so we're going to say, just give myself a string for output here. I'll just reset it to the empty string anyways. So I'll say output is equal to the empty string. If I'm looking at an int, I can already go ahead and put some stuff into my output. What can I put in there? I can say add I space. So I'm going to say output plus equals add I space. So we'll tack that in there. Then I need to get a register, get next available register. So output plus equals that guy, get the next available register. So that'll get me this guy. And then I'll just do it in separate lines. Let's say output plus equals a comma. Comma space, right? So there's my comma space.
And 0.
Oh, and then the 0. So I need this with a space.
But I don't think because after you output everything in C, you say, I don't know, maybe I'm just wrong, but we're gonna read everything into ARM.
You should be able to, because this is giving us this is going to give us MIPC code.
Correct. So I don't think we're using these.
The commas. Yeah, we didn't. So if you wrote it differently, I'm just outputting exactly how they're outputting it.
Okay, all right.
Yeah, you can then convert it, whatever. But if you wanted to feed it directly into your scheme, you could have outputted it a little differently. But it should have been in this style, let's say. So then output plus equals. I'll grab from my data memory. Like that. Okay. And that should be it for if I'm dealing with a int something. We don't have to worry about the variable name or anything, right?
I think you have to think about it.
Only if I execute it.
Well,
In terms of my output stuff here, I don't. When I execute this stuff, I'm just moving stuff between registers and things like that. My executable for this would go through, and it doesn't care that my variable used to be called X. It just cares that I have a value stored inside of T0. T0 is my first variable. Does that make sense? I don't need to know that it was called X here. Later on, if I start changing values of that, I need to know that X was called something.
But you need to know to
For this.
put the value inside.
Correct.
Okay,
Yeah.
all right.
I don't need to know X for this.
Oh, yeah.
For this one.
Yeah.
I'm going to need to know X for this one.
Yeah.
So I'm going to have a mapping for a variable name with its corresponding register. Because I now have a register for that guy, right? So let's see here. Did I already give us something for that? I did not. So we're going to create a class. I'm going to call this guy var environment. And we took in I'll just load him here real quick. This is a register. Hey, you know what I actually can do here? That register will be set in use, and he's in my register collection. Yeah, I'm actually going to get rid of my var environment here. And I'll just hijack registers.
What I tried to do was create a function that would be accessing the last register that was set to in use.
Okay. But since we mark registers as in use, we can then, you could do that.
That wouldn't work.
But that only works if you set the value right afterwards. Because later on, I should be able to say X is equal to something else. Because I could have 500 lines of code, and then 501, I could say X equals 3, which should change a much older register. Right? So in use starts off as false, then this dot var name would start off as the empty string. If, let's see, so set in use. Let's see, should we force it to pass a variable name into that?
well, a register might not useful variable. It can be used for.
Yeah. So then we need to have a set for the variable name. So I'll do source, generate, getters and setters. And I'm going to get a get and set for var name. So now, when I ask for my register collection to get the next available register name, that's in register collection here. This is going to find one that's not in use. So what I'm going to do here is I'm going to have this guy take in a var name. So then when I set something is in use, I can then say this dot the registers at bucket I dot set var name to var name. So once I set it as in use, I can then set it to its variable name. That then allows me to have a second guy here saying public string get register by var name. And what this guy will do is he'll go through all of our registers just like we did here. So he's going to go through all our registers except for register 0, which is our hard-coded 0 register. And then he's going to ask if this register is in use. So if this dot, the registers at bucket I dot is in use, and this dot, the registers at bucket I dot get var name dot equals var name. Ooh, ninja.
You have extra.
Right next to the double equals.
You have extra parentheses.
Oh, I got that.
That's a white.
There we go. All right, so if the current register I'm looking at is in use and it matches that var name, I really didn't have to ask both questions, but this is a real quick question to ask. And this is a much harder question to ask from a resource-intensive thing. Checking to see if a string is equal to another string takes a lot more comparison. So I won't even ask this question unless this part's true. So if the register is currently in use, that means it might be the variable I'm looking for. And if its variable name is equal to the var name, then what do I want to do? I want to return this dot the registers at bucket I dot get name. That's the name of my register. This will get the register, here, what's called get register name by var name. So if I say my variable name is X, it would search through here finding an in-use register that has a variable name associated with it called X, and it would return, in our example here, T0. The register associated with that guy.
And how are we associating this var name with each register?
Down here with get next available register name,
Yeah.
I pass in the variable name now. I say I'm getting a register name right here. I set the register as saying I'm currently using you, and
We're not setting it to. So
Um,
we're resetting it essentially.
well, I mean,
'Cause right now in registers, we would have like the $sign thing, and we're changing that. Is that what?
no, I'm setting the variable name. I updated register. Register now has an extra thing. It has a variable name as well. It has a name, T0, T1, T2. So now if the name was T0, we just set its var name to X. Because I specifically requested the next available register, and I'm going to use this guy for variable name X.
And we have an array of registers.
I already have that. Yeah, that's called my register collection.
So in that array, we have the ability to get var name.
Yeah. In my register array, I have a collection of registers where each register knows its own name, but also knows if it's currently in use and specifically if it's being used for a specific variable name, if I happen to be interested in that. So let's see, where am I at here? MIPS compiler. All right, so that means up here, when I said get next available register name, I would have had to pass it the second half of my, so I'm looking at something that says int, so I need to get the trim of bucket 1.
And also need to train the setting.
So I'm gonna pass this guy, this is, I did trim the first part. This is parts at bucket 1.
You should remove the.
Oh, I see. Because there's a semicolon at the end of it. What he's saying is I trim bucket 1 here. It's going to give me something that looks like that. And I actually have a semicolon at the end of that thing. All right, so let me actually just do this then real quick. String var name is equal to this guy, and then I'll just send it the substring. Actually, let me do it in here. So I'll say var name is equal to var name dot substring from 0 to var name dot length -1.
Why is it parts bucket 0? Wouldn't it be bucket 1?
It is bucket 1. Yeah. So this is my variable name. I'm trimming it to get any spaces. Then I'm going to update my variable name. I want everything from bucket 0 all the way up to, but not including the semicolon. So now I have var name that I can pass in here. So now I got the register name for my output here, but I also let him know about the variable name that's associated with him. Then I outputted the 0, then I outputted this guy, but now my register collection knows that associated with an X is my T0, because I can go back and find that later. If we look at register collection here, here's me get register name by var name. I'll go ahead and do that runtime exception. So this is a new runtime exception. Variable name not found, and we throw that, right? So presumably when I call get register name by var name, I'm going to give it a variable name that would be found. It'll look through all my registers, looking for one that's in use and has a variable name associated with the guy I'm looking for, and he'll give me the name of that register. Okay, so then back here in the MIPS compiler. Here. All right, so this is what I do if I'm looking at an int. I build this output. If I'm not looking at an int in our current compiler, right, I must be looking at the other kind, the other type. And what's my other type? My other type is something that has a variable name, followed by an equal sign, followed by a number with a semicolon at the end. So I'm going to have an output. My output's going to be add I, my next new register, comma 0, comma the value, and then my next line after that will be SW, the register I just created, so I need to remember that one, followed by a comma, followed by 0, followed by the name of the register that the variable name I found that I'm looking at is stored in. All right, so we'll start building this guy up. So we're going to say output, add I, then I need to get a new register. So I'm asking this guy for a register, but this guy's not actually associated with a register with a variable name. He's registered with an immediate value, right? So I'm using this to temporarily store an immediate value. So we're going to call this guy temp immediate. Actually, what we probably just did there is we have now a keyword in our language. We're not allowed to have a variable named underscore temp immediate underscore.
Yeah, but you can actually using a illegal C variable name.
Yeah, with the underscores. Yeah, so this makes it not legal for C, starting it with an underscore.
It's not allowed in C.
Not starting it with an underscore.
That's a C thing? Or
Java too. I don't think you could start a variable name with an underscore.
Oh, I see what you're saying.
Yeah.
I know I tried.
Yeah. So bottom line here is, I mean, and well, you definitely can't start it with a number. You know, so whatever you want to do here, we're just, we're giving it a variable name that can't exist. So it's safe for us to label this. Here we'll do the 1337. Isn't that leet? It's the geeky leet thing. Underscore LOL.
What the
Yeah.
1337 means to?
LEET, leet speak, like old. It's an old gaming thing. Just roll with it.
No one's.
Okay.
Yeah.
We don't know.
It's an old thing. If you look up leet speak later on, you'll know what I'm talking about. It's like back from like MUDs, like text-based games. But in any case, I'm going to grab my next available register. I'm going to give it a fake variable name because I don't actually need to this guy as a variable name. So I get his name, right?
Mm-hmm.
Oh. Then
Add the 0.
what I need to add next, now I need to, so that's the guy, so now I need to add a comma, 0 comma space. So output plus equals, comma, like that. Then I need to get my value. My value will be the bucket. So it's kind of like the thing I did before.
Bracket 1.
So it's this guy right here. So this is var value. And var value. So that'll get me my number without spaces with the semicolon removed. All right, so parts 1 trim, no spaces. Then give me everything but the semicolon. So that'll, in this case, give me my 7, and this is var value. All right, and then I concatenate that on. So this is output plus equals var value. That gets me here. Now I want to kick it down a line. So output plus equals \n. Then I need to do a SW. Now I need to have remembered this name of this register. So I need to say up here, string temp reg name, and we're going to set this guy equal to him. And then I can put temp reg name here. Because I'm going to need temp reg name again here in a second. So once I kick it down a line, I'm here, so I need SW space. Followed by my temp reg name. followed by comma, space, 0, open parenthesis. Followed by, now I need to look up my other variable name. So I'm going to say string old var name. Actually, I need old reg name. And my old reg name is going to come from this dot the register collection dot get register name by var name. And that var name is going to be called parts at bucket 0.trim. Yeah. So my parts at bucket 0
That's gonna get the X.
yeah. So I'm looking at a line that looks like this. So parts, this is going to be bucket 0. This is going to be bucket 1. Well, with the semicolon. So I'm taking bucket 0 dot trim, which just gets me the I. So that's the name of my variable. I'm saying give me the register that was assigned that variable name. So that's what this guy does. I'm asking my register collection to get me a register name by a variable name, and the variable name I'm passing is parts0.trim. And then we have our last piece here, just closing with a parenthesis. So output plus equals closing parenthesis.
You have to actually add your reg name.
Oh, thank you. I'll do it in 2 separate lines just to stay consistent. All right, so one way or another, I have built up output for my first form that starts with an int, or I've built up output for my second form. So now I'll go ahead and display output. We'll just print it out, system.out.println output.
You have to, okay.
And output gets reset before each other one. So the next time around, when I read in my next line that's not EOF, I will empty out output, go through this whole process again, and fill up output with either an add I or, well, fill output up with one of these two things. Each time I'll spit out the value of output.
Your line 29 has that bug.
We will see.
And you still have the infinite, right?
No.
So because 28 is
Well, whatever
split
we-
by
Right here.
equal, the 28 line you split by equal, but in I there's no equal. So when you check if the part 0 equals to int, it
Yeah.
will not be int. It will be int space I.
Oh, yeah.
The first one.
We can still split it on equals. That's fine. But
the
it
thing is, you should be split by space for the first check. For the int.
we can, or we can still do it this way. So if we're splitting on an equal, what he's saying here is
You
that
can only say start with.
my entire part bucket 0 will be that.
Yeah.
That's what my entire part bucket 0 will be.
You can only say start with, or you cannot.
Yeah.
say equals.
So instead of saying, does this guy equals int, I can do the starts with thing that looks for that. But even then, when do I get my...
You still have your bar name that you have to split
Yeah,
by space.
so here. Easiest thing to do is I'll split this on space. That'll get me those pieces quickly.
Yeah,
Then what I'll do is if I'm in the other part, if I'm in this else, I'll just go ahead and split on equal sign.
yeah.
So I'll just resplit. So I'll split on spaces first, then I'll ask, is bucket 0 an int? If it is, then I'll do the stuff I was doing anyways. So if I split on a space here, bucket 0 will be int, bucket 1 will be that guy, which is the way I did my logic anyways. Otherwise, it must be my other form, so I'll just go ahead and re-split it on an equal sign. So all my logic is the same as we were doing it. We were just making the assumption that splitting on an equal sign would make me look at the beginning part as int when it actually did not split it into anything if there was no equal sign present. And there's our output. And then if I just add one more line to this guy, later on I say I is equal to 2, let's say. That should go back and use T0. See my T0 there? So he was able to look it up. So this guy should support an unlimited number of variables and up to the number of registers we have.
It's not exceeding the.
That's fun.
Yep. All right, so for your homework, we're going to do more of this.
Wishful thinking.
Because we just did everything in the assignment section, right?
Yeah.
Sounds so long.
We're having more. I don't think the rest are easier.
All right, so for next week, we want to do the assignment, z equals x plus y.
Don't you wanna do with us?
I'll do it next week.
Much fun.
Hey, it's going to be pretty easy. I'll give you my code as a starting point. Yeah, so that should be fine.
Just that one time.
No, we need more than that.
I will be contacting you sometime about getting my run configuration set up.
Are you still stuck?
Yeah, it's literally broken on everything. It's broken
All right.
on Eclipse and on Android Studio, and it's completely broken on Android
So
Studio
weird.
before. So I must have like. I don't
So
know, deleted
this is what I'll do. I'll give you expressions, and then for next class we have to do the memory stuff. So read chapter 6, do expressions. All right, just do expressions. In my code, just do expressions, and then next time we'll write we'll write the rest of it. Sound good? But there's like a legitimate risk of a quiz over what we talked about in class today.
up to where we stopped.
Up to where we stopped.
So all that fun circuit stuff.
Yeah.
Is everything teal today, or is like everything?
Is who?
What do I say? The quiz about everything we'll talk about today, or is like.
Yeah, everything. So potentially, so there will be a very strong possibility of a quiz involving what we talked about in class today. And then you only have to implement expressions, all the stuff from expressions here. So it should fully support expressions.
And you'll put that up on Blackboard.
No. Absolutely not.
Poor Alexis. Poor Dream. I just have to guess what the homework is.
So I mean, that homework